Welcome back. In this lecture, we will look at water and thermal management in the context of solid oxide fuel cells. Water and heat are continuously generated when the fuel cell is operating. So, to maintain steady state, they have to be removed to ensure steady operation. But the question is, in addition to these two being removed, can we integrate water and heat generated back into the system uh, to productively use both water and heat? We would look at how this can be done. As mentioned in an earlier lecture, typically hydrogen is generated by reforming reaction. This is an example of a methane steam reforming reaction, wherein the products are carbon monoxide and hydrogen. In the context of solid oxide fuel cell, not only hydrogen, carbon monoxide can also act as a fuel. However, there is a side reaction which has a debilitating effect on the performance of solid oxide fuel cell. Carbon monoxide and hydrogen can form solid carbon and H2O. This reaction is referred to as a coking reaction. This solid carbon that is formed may deactivate the catalyst and significantly decrease the performance of a fuel cell. So this side reaction has to be suppressed. As you may notice, this is a reversible reaction indicated by this symbol. Therefore, if you have a lot of H2O in the system, you can have the reaction go in the backward direction and have the balance mostly in the form of carbon monoxide and hydrogen and not in the form of solid carbon and H2O. So you want to have a way of adding H2O. In the context of fuel cell, you have H2O readily formed as a product of the central reaction. At the anode, O2 minus reacts with H2 to form H2O and two electrons. So we can supply part of H2O that is being formed back into the system, therefore, to suppress this reaction. There is an additional reaction because carbon monoxide can also act as a fuel. In this case, O2 minus reacts with carbon monoxide to form carbon dioxide and two electrons. Because H2O is an easily condensable vapor, so one way to recycle back water is to use a heat exchanger. When you remove some heat, water vapor get condensed as liquid water, and this liquid water can be supplied to the reformer to suppress this reaction. This involves removal of heat, which but remember that this reforming reaction is an endothermic reaction, which requires heat to be supplied to the reaction. To efficiently do this, in the sense that you do not want to be supplying external heat, there is another way of recycling H2O. You can, without condensing the water, that is, without removing the heat, you can supply the water vapor that comes out of the as an exhaust from a fuel cell, and this can be water vapor itself can be put back to the steam reformer. It does two things. It not only supplies H2O, it also supplies heat back into the steam reformer. Thereby, the need for external heat to run this endothermic reaction is not required. Most of engineering is about trade-off. This approach, as opposed to this approach has certain um, benefits and disadvantages. First, it facilitates heat integration. That is, there is no need to add external heat. Heat generated inside the system or the source of heat inside the system can itself be utilized for running the endothermic reaction in the reformer. However, when we try to do this instead of this approach, the compressor that is being utilized has to be it has to be a high temperature compressor, which can be more expensive than this simple compressor. In addition, when you recycle the entire exhaust, it also decreases the concentration of H2 and carbon monoxide in the reformer when the entire exhaust is recycled back. In the next lecture, we will look at water and thermal management in the context of proton exchange membrane fuel cell. Thank you.